Hey guys, so this video is a continuation of the previous video where we had discussed the double structure of a random variable. And in this video, we're going to prove that the mean of the distribution of x is equal to the mean of the distribution of x bar. So the expected value of x we already know is mu x, right? And in this video, we're going to prove that the expected value of x bar is also equal to mu x. So basically we're proving that the expected value of x is equal to the expected value of x bar, which is equal to mu x. So let's begin. Okay, so the first step is simply going to be plugging in for the definition of x bar. And I'm just going to write that over here. Let me just erase this so that we have more space. Okay, cool. So by definition, we know that x bar, our estimator, is equal to 1 over n times x1, and these are x's in uppercase, okay, all the way till xn. Okay, now all we have to do is plug in for this. So when we do that, we get, so the expected value of x bar is equal to, we're taking expectations on both sides, the expected value of 1 over n times x1 plus x2 plus all the way to xn. Okay, so all we have done is that we have plugged in for x bar. Okay, cool. So in the next step, I am going to use expected value rule number 2 to take out 1 over n as a common factor. Okay, so using EV rule 2, as always, we should explain why we're doing what we're doing. So we're using EV rule 2. Okay, so the expected value of x bar is equal to 1 over n times the expected value of x1 plus x2 plus all the way to xn. Okay, cool. So now we can use expected value rule number 1 to further simplify this. So using expected value rule number 1, we can break up these components. So let me just do that in the next step. So this becomes 1 over n times the expected value of x1 plus the expected value of x2 plus all the way till xn, so the expected value of xn. Okay, cool. In the next step, now this is where it gets a little bit tricky, and we have to explain, as always, why we're doing what we're doing. So we have to write an explanation. So let me first explain. Now we have to remember the fact that at the planning stage, the expected value of x1, okay, let's focus on x1 for now. At the planning stage, as a beforehand concept, the expected value of x1 is just mu x, right? And the same is true for all of the other components, that is x2 and all the way till xn. As a beforehand concept, the expected value is always going to be mu x, right? So we can now just note the explanation for this and then we will move on. So as a beforehand concept, let me just write this on the right hand side. So at the planning stage, the expected value of x1 is equal to mu x as a beforehand concept. Okay, and the same is true for all of the other components. It's true for all the other components, right? So therefore, this becomes 1 over n times mu x plus mu x plus all the way till xn. So this is also just mu x. So now we can notice that we have mu x n number of times, because n is the total number of the potential observations, right? So the potential distribution, sorry. So this simply becomes n times mu x over n. And the n is going to cancel out, so all we're left with is mu x. So we have proven that the mean of the distribution of x is equal to the mean of the distribution of x bar. So this is expected value of x bar, which is equal to the expected value of x, hence proven. Now in the next video, we're going to prove that the variance of the distribution of x is greater than the variance of the distribution for x bar. Okay, so let me just erase this and rewrite this. So in other words, we're going to prove that the variance